And I have here section 6.1. Of course, I will be putting additional sections as time goes, yeah? But again, that's section 6.1. So let's open this and we will start using this. So you see integration by parts. What? I probably opened the wrong file. Let's see. Okay, integration by parts. So the starting point for this formula is product rule. The derivative of the product of two functions, f times g derivative, is, you know this of course from last semester, is f of x g prime of x plus f prime of x g of x. So that's a starting point. That's a product rule for the derivative. Now, let's integrate this equation.
Professor, you're not sharing your screen.
Not sharing the screen?
No.
Let me see. One moment, sorry.
Awesome, thank you.
Now it's you see this now, yeah?
Yes.
Okay, so something happened. Okay, so if something like this happens, just of course let me know. So again, we have a product rule for the product of two functions. Derivative of the product f g prime is f g prime plus f prime g. So that's a product rule from the last semester. Now, if you integrate both sides of this equation, well, integral from this is equal integral from this plus integral from this. Now, as you know, derivative and integral cancel each other. Integral is the inverse operation to derivative. So integral from the derivative cancels each other, and what's left is the function under the integral. So f of x g of x is integral f of x g prime of x plus integral f prime of x g of x. And now you can solve for this, or you can solve for this, and this leads to this integration by parts formula. If you solve for this, you will see that the integral f g prime is equal fg minus f prime g. So that's one integration by parts formula. But you can solve for this and you have a variant. So integral f prime g is fg minus fg prime. So again, to remember this, you have fg prime and here is fg and here is the other way around, f prime g. So those are integration by parts formula. You will see how it works in a moment. Well, usually it's probably easier to remember kind of shorthand notation. Basically, integral fg prime is fg minus integral the other way around, so f prime g. So that's this formula. Or integral f prime g is fg minus fg prime. So both are useful, kind of sometimes you use this one, sometimes you use this one, depending on the situation. So those are integration by parts formula. Of course, goal is like this, that if you have some complicated integral here, if you use integration by parts, you hope you'll get something simpler here. So kind of you have something complicated here, and hopefully you'll end up with something simpler here. And you'll see that that's maybe the case in many cases. So let's look at the example. Well, okay, I will just maybe do this on the whiteboard as well. Or maybe, okay, maybe next on the whiteboard. So let's look here. We would like to compute integral from x sine x dx. Well, so let's make this assignment. I will assign that x is function f, and sine x is g prime. Now you can make different assignments, and kind of sometimes it's not clear how to make those assignments. There are no general rules and so on. Kind of just you try something and you hope that this will simplify things. So in general, it's not clear in general how to make those assumptions. Kind of when you solve all the web work problems, you probably have enough experience, and you'll get some feeling kind of what you should do. But okay, so let's call x to be f and g prime is sine x. Of course, if g prime is sine x, g is minus cosine x. G is minus cosine x. So using integration by parts formula, you remember it was fg. Well, so f is x and g is minus cosine x. So this is fg minus, not here, fg minus, it's part of the formula. And now f prime is 1. So 1. And g prime, and g is minus cosine. So minus cosine. So minus gives you plus, and we have that this thing is equal to minus x cosine x plus, yeah, minus is plus, cosine x dx. Integral from cosine is sine, and we are getting our answer that integral x sine x dx is minus x cosine x plus sine x plus, we finished, we can put constant of integration if you want. You remember that this constant on the web work will be already, the system will put this constant for you, but doesn't matter too much. Yeah, so kind of constant of integration. Okay, so that's first example how to use integration by parts. Let's do the other example on the whiteboard. Kind of, it's interesting. You would like to integrate natural logarithm x dx. How can we integrate natural logarithm? So let me go, and I will illustrate this on the whiteboard. So we would like to integrate ln of x dx. Well, we don't have two functions, so let's introduce function in an artificial way. Well, let's write this like this: 1 times, nothing changed, yeah, but I just put 1 over there. Now we have two functions. Formula for integration by parts have two functions, so 1 and ln of x. And now let's make this assignment. I will call this f prime. So 1 is f prime. And ln will be g. So we have, you see, we have integral f prime g. We have integral f prime g dx. So we can use integration by parts formula. Maybe now that's a first example or second, so let's maybe write here. What is f? So of course, if f prime is 1, f is x. And if G is ln of x, G prime is 1 over x. Usually you do those computations in your head, but that's maybe second example, so let's put everything here. So now let's use the form for integration by parts. So you see integral f prime g is fg first. Well, f is x, and the g is ln of x. So this is fg minus, you remember minus is part of the formula, integral, the other way around, f g prime. Well, f is x, and g prime is 1 over x. Well, so you see now that x cancels, and the final answer is x ln of x minus integral from 1. That's 1. Well, integral from 1 is x. Well, we finished. We can put constant of integration if you want. Now, that's useful formula kind of, and you'll see that you'll encounter this quite often when trying to compute something. It's probably a good idea to remember this if you can. So here is the formula. X ln of x minus x plus constant of integration. Again, that's maybe useful to memorize this kind of, because when you get this, you don't have to do this again, just you can use just this formula. So that's kind of how these things work. Now, maybe that before I go to slides, let's discuss one other example here on the whiteboard. This other example will illustrate that in order to compute something, sometimes you will have to use integration by parts more than once. So this example, you will have to use it twice. So let's say we have t squared e to the power of t dt. You would like to compute this. So f, we call t squared f. You could call this f prime, you will see that this will not help. So f is better. And this will be g prime. So we have f g prime this time. Yeah, we are using this variant. Okay, so that's equal to what? Well, that's fg. Well, f is t squared. If g prime is e to the power of t, g is also e to the power of t. So that's fg minus integral. Well, f prime g, the other way around. F prime g. F prime is 2t e to the power of t. Okay, so let me erase this. And let's write it. And so what we got so far is t squared e to the power of t minus factor out 2. 2 is a constant, we can factor this out. Integral t. Okay, we are not done. But you see here we have t squared, now we have t only, so kind of it looks that simpler. Let's do this one more time. So let's apply integration by parts one more time. Well, so again, f, and this is g prime. So that's equal to t squared e to the power t minus 2. Again, fg. Well, fg is t e to the power t. That's fg minus integral f prime g. F prime is 1, and g is e to the power t. And of course, you see that integrate from e to the power t is e to the power t, so this we can integrate this, so we can get rid of this. And that's the answer. Well, we finished. You can add constant of integration if you want. Yeah. Again, as I mentioned, on the web work, usually this is done for you automatically. So that's the answer. Of course, you can kind of multiply, you can simplify, and so on, kind of, yeah. But you can put this thing like this in the web work, and web work should accept it. Okay. So let's discuss next example on the slides. Okay, so this is the example we discussed. One other example. This next example also will illustrate something different. So we would like to integrate e to the power x sine x dx. Okay, so let's make, usually this is kind of strange example. So let's call e to the power x to be function f and sine x g prime. So if, of course, if this is g prime, this means that the original function g is minus cosine. It's minus cosine. Let me see if I will, okay, one more. Okay, let me see what was here. Okay. So you see, this is f and this is g prime, so g is minus cosine. So using integration by parts, we have fg. Well, so f is e to the power x, and g is minus cosine x. So minus e to the power x is the cosine. So this is fg. Minus, so I put here plus because we have minus, and then this minus will give you plus. So minus integral f prime, well, so f prime is again e to the power x, and the g is minus cosine. So that's why I got plus here, because I have minus and minus cosine gives you plus. So what's the kind of conclusion? In order to compute e to the power x sine x, we have now to compute e to the power x cosine x. Well, okay, let's do this again. So once more time, again, so this, let's call e to the power x f, and cosine x is g prime. So this time g is sine x plus sine x. So that's equal to, well, I repeat it, minus e to the power x cosine x plus. And now fg, so that e to the power x sine x, that's fg, minus is part of the formula, f prime, which is e to the power x, and the g is sine x, should be dx here. Well, so, okay, so that's what we got. So in other words, doing those things, integrating by parts twice, we got to the conclusion that integral e to the power x sine x dx is minus e to the power x cosine x, plus e to the power x sine x minus integral e to the power x sine x dx. So it looks kind of crazy because in order to compute this, we have to compute this, the same thing. However, that's useful. This is useful because you see that here we have plus sign and here minus sign. So we can take this on this side, we can move this on this side, and we get twice e to the power x sine x dx will be equal to this. So twice of what we want to compute. So if you divide by 2, you get your answer. So e to the power x sine x dx is 1/2 of this and this. So e to the power x sine x minus e to the power x cosine x, well, plus constant of integration. You can, if you want, you can factor out e to the power x, and that's the answer. So you see, it's kind of circular exam, looks like catch-22, but still it's useful. You integrate by parts twice, and because the sign comes right, we get that. Of course, if you would get here plus, this would not be helpful, but we got minus, so it is helpful. Okay. So now, next thing is integration by parts. We can also have integration by parts for definite integrals. So we start the same way. To derive it, we start the same way as before. Let's write a product rule for derivative of two functions. Let's write it d over dx this time. So derivative of f times g, of course, you know that that's f prime g plus f g prime. Now let's integrate both sides of this equation, but let's integrate from a to b. So integral from a to b, integral from a to b, integral from a to b. And now look here, again, we have integral and the derivative. This cancels again, so kind of that, because that's inverse operation. And what we get this function that's called antiderivative, but kind of we get the function f of x dx, but this time we have to take it from those limits from a to b. So kind of this will be f of x g of x from a to b. In other words, this is f of b g of b minus f of a g of a. And then if you compute, for example, this one, if you solve this equation for this, f g prime, we are getting this integration by parts for definite integrals. Integral from a to b f of x g prime of x dx is in f of x g of x from a to b minus the other way around, f prime g. Of course, you can solve for this and you get another variant. Yeah, so you have, of course, another variant. F prime g will be this minus f g prime. I just wrote only one here. So let's illustrate this on some examples. So here, and again, let me do this on the blackboard, on the whiteboard. So let me stop sharing for a moment. And let's go to the whiteboard. Where's the note? One moment. Okay, so maybe first we'll be using arctangent. What you have to know again, of course, you know this, it's 1 plus x squared. So kind of you have to know that the derivative of arctangent is 1 over 1 plus x squared. And in your book, usually they write arctangent plus tangent minus 1. That's the same thing. That's arctangent, okay? But that's the notation I think you have in your book. I think the web book is using arctangent, but your book is using tangent minus 1. Okay, so that's the formula we will need in a moment. And now let's try to compute integral from 0 to 1, so definite. Let's use arctangent, okay? No, maybe let's use this other because we'll be able to squeeze things on one line. So, okay, tangent minus 1x dx. Again, we have only one function, so let's introduce the other function in artificial way. So tangent minus 1x, 1 dx. And now let's call it f. So tangent minus 1x, or arctangent is f, and the g is 1. So I make this designation. So that's equal to, well, g prime. G prime, f g prime, yeah, f g prime. So f g, if g prime is 1, g is x. So x tangent minus 1 x. Well, but formula tells you in those limits from 0 to 1 minus integral from 0 to 1. Yeah, now definite integrals. F prime g. Well, f prime, you remember I put this, it's 1 plus x squared. That's f prime. And the g is x. So now to continue, we have to okay, we will compute this number one, to integrate this. Well, we will use substitution. Let me put it here, maybe just try to squeeze it. U is 1 plus x squared, okay? So that's u. So du is 2x dx. So I need 2. I put here the 2. In order not to change anything, I divide by 2. So I just because I have 2x dx, I have 2x dx, that will be du. And of course, in order not to change anything, I have to divide. So I just multiply by 2 and divide by 2, no change. So that's equal to substitute 1 times tangent minus 1 of 1 minus 0 times whatever 0. So that's this. Minus 1/2 integral, well, du over u. And now, of course, the limits may be changed. And then, so let's see. If x is 0, u is 1. So this limit becomes 1. Let's write it kind of in blue. That's 1 now, yeah? So it was 0 for x, but if x is 0, u is 1. And if x is 1, u is 2. So this integral now goes from 1 to 2. So that's equal. So now, what is arctangent 1? Who remembers? Arctangent 1.
Isn't it pi over
Pi by
4?
Yes. So that's pi over 4. The arctangent of 1 is pi over 4. Minus 1/2. Well, that's ln of u, absolute value of u. So ln, absolute value of u, between 1 and 2. Let me erase this thing so you see things. Okay, so you substitute. Let me maybe erase things somewhere above. So the final answer is pi over 4 minus 1/2, well, ln of u minus ln of 1. ln of 1 is 0, so minus just ln. Absolute value of 2, of course, is 2. So that's the final answer. Of course, if you want, you can put this 1/2 under the logarithm, and that's also will be correct. So another version is pi over 4 minus ln square root 2, whatever you prefer. So that's how this works for definite integrals. Okay, now this is a short section. I will try to start also next section today, but before I do this, let's go and comment on homework problems, okay? Now, in your book, the substitution rules are also written in different ways, so maybe let me write it here, kind of also what you have in your book. F G prime so that's what we used, and of course you have this in your book. But in the book, they sometimes write this rule also in such a way. Let's call it U, and G prime of X is dV. So if you call V is, if V is G, kind of dV is G prime dx. That's equal to UV minus integral and the other way around. So V du. Again, I don't like this notation. I prefer this one. But in your book, you have also this one as well. So again, if you prefer this one, that's fine. But for me, this is kind of more convincing, and I prefer this better than this. But that's another variant of the rules. I'm mentioning this because the solution to homework problems, unfortunately, is using this thing I don't like, okay? So just when we comment, usually this will be done, but you'll be able to follow anyway. So now let's look at some homework, see kind of how things work there. So I will stop again, so I will share the screen, and let's go to homework problems. I get web, work, and so on. You should see it. Now I go to here. Again, we will not solve the homework problems. I will only comment how to start. Some of them are quite involved. There's a lot of computations, kind of, but only we just discuss kind of more or less what to do. kind of the idea how to start the problem. I will skip, so we will not solve this completely, just only discuss it a little. You see, that's not too many problems, just 11. So only 11 problems. And again, more or less, all of them are, well, maybe kind of just more or less all of them are okay. So x e to the power 3x dx, more or less what we had. You remember we had this t squared e to the power t, then we integrated once, we have t e to the power t. So this is more or less what we have. But now they explain this using this different notation. So look, again, that's the notation really I prefer the other one. But okay, so you call this u, and this is dv, u dv. That's the formula. You see, u dv is uv minus v du. So kind of that's another variant on kind of the integration by parts in somewhat different notation. Again, some people like this notation, I don't. So kind of let's call u is x, and this is dv. If u is x, du is dx, of course. And if this is dv, the v is 1 over 3 this, because of course, if you compute the derivative of this, you get this. So using the notation, kind of, you substitute and you get this. Of course, now you can integrate and you get your answer. Anyway, we'll be not solving things, only how to start. So later, when you kind of look at the solution, when the solution will be posted, you will have this notation here. So the webbook is using this variant of rule instead of the first one. So just let's go briefly fast over those problems. So of course here more or less what we had already. You remember x, we had x sine x or something. So that's the same idea. This will be u dv, and this will solve the problem. So here, of course, it is this, yeah. Clearly, that's u, and this is dv. So if this is u, du is 4 dx. And if this is dv, the original function is sine 5 of x, or of course 1 over 5. If you compute the derivative of this, of course, you get this. And then you see you substitute, of course, and so this is not too many, but you see that some problems are quite involved. Here, again, ln, we had already ln, but here we have 8x plus 4. You can make, again, 1 times, and then u is 1, and this is dv. And this is v. But to solve this problem, probably it would be easier if you first make the substitution 8x plus 4 equal, let's say, w or something. So I think this problem would be easier to solve if you start with the substitution, but they don't. You see that's why computations are quite involved if you don't use substitution. So again, u is this, and dv is v is 1, dv is x, so v is x, and you get this. So you see, quite involved. So I think that it would be easier to solve this if you make substitution first. Do substitution first, then you'll get this ln of w, what we had here in class, much simpler. Here, if you don't do the substitution, you see, it's quite messy. But of course, it's not too bad. Arctangent, well, we had this example, yeah? We have arctangent x, here is TuTh, so kind of that's more or less the same thing. Well, again, we had e to the power x sine x, same thing, so kind of you integrate twice. This is the sketch 22 problem. You integrate twice and get it. So here you see, you have to do this twice. You see, 1 and then second time, yeah. So again, some computations, but more the idea what we had already. So let's see what they recommend. You put u equal ln of x, and 1 over x to the power 4 is dv. And you see that this will work. But again, some computations, as you see. So it's not completely trivial, yeah. Same thing, you put here u, and then this is dv, it will work. Okay, you have 11 problems, kind of just more or less all of them are kind of easy to guess kind of more or less what to do here. For problem 10, they suggest first make substitution for x to the power 4. This will simplify things a lot. So in this problem, make first substitution, u equal x to the power 4, and after this only use this. And the last problem, again, so in the last two problems, make substitution first. Let's say u is equal 4 square root x. This will simplify things. Okay, so I would like to start trigonometric integrals, because that's a very long section. So let's start, and let's start today. So trigonometric integrals and trigonometric substitutions. So again, we will go to, I will go to here. I go to Canvas, my class, files, and now section 6.2. So we just start things. That's a long section. We will not do everything, just let's start. Again, there are no rules, no general rules how to deal with trigonometric integrals. We will be using a lot of trigonometric formulas. We will be using integration by parts. We will be using substitution and so on, kind of. So we will try to combine a lot of things, but in general, there's no rules how to do trigonometric integrals, only in some special cases. And we will just go over a few examples. But again, if you solve all the web-book problems, you'll get enough experience to deal with such things. So first one is, we would like to compute integral cosine cube x dx. Well, how to deal with this? Well, let's write cosine cube as cosine square and cosine. That's the same thing, of course. And now, let's use the most basic trigonometric formula. You know that sine squared x plus cosine squared x is equal to 1. So in other words, cosine squared x is 1 minus sine squared x. So I will replace cosine squared x by 1 minus sine squared x. Why this is useful? Well, because if you now make a substitution for sine, you'll be able to get rid of cosine. So you see, making substitution u equals sine x du. Let me see if someone is waiting. So you see, if I make substitution u equals sine x, du is cosine x dx, and I will be able to annihilate this thing here. So making the substitution, we have integral 1 minus u squared du. Well, that's a polynomial, easy to integrate. So this is u minus u cubed over the 3, well, plus constant of integration. And u was sine x, so if you substitute, this integral is sine x minus 1 over the 3 sine cube x plus constant of integration. So you see, we use trigonometric identity. Well, here you have more complicated things, but still we can do things more or less in the same way. We have integral sine cube, sine to the power 5 x cosine square x dx. So in this case, the idea is, well, let's write sine to the power 4 as sine to the power 5 as sine to the power 4 times sine. So that's sine to the power 5. Cosine square. And now sine square is 1 minus cosine squared. So sine to the power 4 is 1 minus cosine squared squared. And then cosine squared sine. Of course, now you see that's useful because if you substitute u equal cosine x, you'll be able to get rid of sine. So u equal cosine x means du is minus sine x dx. I put here minus minus, and this integral becomes minus, because it's minus here, minus 1 minus u squared u squared. And that's equal. Well, I didn't finish, but that's a polynomial. So of course, you can expand it. This is 1 minus 2 u squared plus u to the power 4. You multiply by this and you integrate term by term. So that's easy to do. So it's just, once you reduce things to the polynomial, more or less you are done, because integration of polynomials is easy. So see, we were able to reduce this trigonometric integral to integral from a polynomial function. Okay, so here there's some forms we have to use. So maybe let's discuss it, and I will put here maybe let's go on the whiteboard, and I will introduce some forms. We will need a lot of trigonometric formulas. The names are like this: double angle and power reduction formulas. Sometimes you will need sum or difference formulas. You may need product to sum formulas or sum to product formulas. So there's a lot of formulas. Now I will be introducing those formulas when they need for them arises. So just not all of them at the same time, but just one by one. So let me now go to the whiteboard. Okay, so let's say that that's, what is this? What is my piece of paper? Yeah. 15. Let's say that you would like to compute integral from 0 to pi, so definite, sine square x dx. When you have square here on higher powers, that's somewhat complicated. So we will need something that is called double angle and power reduction formulas. Okay, so of course everybody knows sine 2x double angle. Well, that's 2 sine x cosine x. That's a famous formula, and we'll be using this quite often. And we have for cosine 2x. Well, it's cosine squared x minus sine squared x. So 2x, and here is x, x. Yeah, so that's double angle. Those are double angle. But for cosine L2x, we have three variants. Another one is 2 cosine squared x minus 1. That's another one. Or still another one, 1 minus 2 sine squared x. So those are double angle formula for sine and cosine. You have also double angle formula for tangent. I will not write it here, but tangent 2x is 2 tangent x divided by 1 minus tangent square x. But those are the most often used. Now, if you solve this equation for cosine square x or this equation for sine square x, you get the following. So let's do this. I will solve this equation for cosine square. Well, so cosine square x is 1 plus cosine 2x over 2. And of course, this is called power reduction formula because you have power 2 here, and you have, of course, double angle, but you have power 1. So power 2, power 1. So this is called power reduction formula. Well, if you solve this equation for sine squared, you get another power reduction formula for sine. So sine squared x is equal to 1 minus cosine 2x over 2. So those are power reduction formulas. And you see that this formula will help us to evaluate this integral. So in order to evaluate this, we will need this formula here. Okay, so let's continue. Equal. Well, 1/2, we can put 1/2 in front. That's a constant, yeah, 1/2. So sine squared is 1 minus cosine 2x dx. So I used this formula, and of course, so you see now, of course, easy to integrate 1, and now you integrate cosine to the first power. So let me maybe continue here. So let me erase now those formulas. And this is equal to 1/2. Well, integral from 1 is x, from 0 to pi. So that's this integral. And integral from cosine is minus 1/2 sine 2x. Well, check it. If you compute derivative of this, you get this. If you don't see it, put here, first integrate this by substitution, put here 2x equal u, and so on, kind of. If you don't see this right away, do this by substitution. And of course, you see now that if you put here pi will be sine 2 pi. Sine 2 pi is 0. If you put 0, that's sine 0, still 0. So this term is 0. And the final answer is 1/2 times pi. So pi over 2. Now, let's discuss what we would have to do if you would have something more complicated. Let's say you have to the power 4, okay? We will not finish this, but let's kind of see how to deal with this. Well, then you will have to use this kind of power reduction formula twice, as you will see in a moment. So kind of, again, that's equal to, let's try to deal with this. Okay, sine squared, this is sine square square. Now sine square using power reduction, that's what was over there, this was 1 minus cosine 2x over 2 square. Yes. This is sine square. So you see again, we use power reduction formula and we got this. So that's equal to, well, 1 over 4, you can factor this out, over 4, integral from 0 to pi, 1 minus cosine 2x squared. So if you square it, it will be 1 minus 2 cosine 2x plus cosine square 2x. So you see, of course, we are still not done, but you see that, easy to integrate 1, no problem. Well, easy to integrate this one because we have first power. So now we have to integrate cosine squared. So let me maybe write on top and we will just, I will explain how to integrate this last piece. So what we have to, well, there'll be 1 over 4. Again, this we know how to deal. So there'll be integral cosine squared 2x. So you see, still we have to integrate cosine squared. Well, so what you do? Well, you use power reduction one more time, namely cosine squared 2x is 1 plus cosine twice as much, 4x over the 2. So just let's concentrate on this one. Let me erase this. We have to deal with this. Yeah. So of course now this thing now becomes 1/2 integral 1 plus cosine 4x dx. So of course we have first power. And integral from cosine is minus sine. So okay, the limits I forget. What was 0 to pi, I believe. Yeah. So let me erase it and put here. So this integral now is 1/2. This was, we remember, x from 0 to pi, so that's pi. And minus 1 over 4 sine 4x from 0 to pi. You can check it if you plus. If you compute the derivative of this, you get this. Yeah. this is cosine 4x times 4. We cancel here and we get cosine. And of course, again, if you put pi will be 4 pi, which is 0, and if you put 0, it's 4 0, 0. So this is again 0, and the answer is as before, pi over 2. Okay, so maybe that's enough for today, but we will have a lot of other examples and a lot of other identities. So I'll be putting those identities as we need them. When the need arises, I will put, but kind of those identities I put today, try to just put them somewhere and maybe kind of be aware that they exist, kind of, yeah. Power reduction formula, double Young formula, very useful to integrate to compute trigonometric integrals. Can you hear me?
Yes.
Okay, so let's stop at this moment. So again, we will probably I stop at the same moment as this other class, so I don't want to go ahead. So kind of let's and see you again on. Now I extended web work, this interaction to web work homework, but it's due I think today by 10 p.m. If you didn't do this yet, try to do this today. The first homework is due I think today at 10 p.m. So thank you very much.
Thank you.
Thank you.